So what is hysteresis loop, and what is hysteresis loss as a result of this hysteresis phenomenon? So in all ferromagnetic substances or magnetic substances, as we discussed in the last topic of magnetic field strength, whenever you produce a current in an electromagnet, magnetic field intensity, magnetic field strength is going to increase, as well as the flux density is going to increase, or flux in general is going to produce. Now, if you have a ferromagnetic substance that is not magnetized, or if you have an electromagnet that is not magnetized, and you start supplying current to that substance, or in other words, you start applying magnetizing force or magnetic field strength. So you start supplying current to an electromagnet. Right now you don't have any magnetism. So when you start supplying current, of course, then the flux density, which is on the y-axis, starts increasing as the current starts increasing, and at one point, of course, it starts getting saturated. So from point the origin to this point A, let's say it's close to the saturation. Now, when you remove the current, when you disconnect the electric source that was supplying the current, the general idea would be that the curve is just gonna come back, that the flux density is just gonna become zero when you turn the magnetizing force to be zero. However, it does not exist. It does not happen. What happens is the poles, the what we call magnetic dipoles, that are arranged due to the supply of current, those dipoles do not become totally disoriented even if you remove the current or magnetizing force. There are some alignment still left in the dipoles, and due to that alignment, the magnetizing force does not go down to zero, the magnetic flux does not go down to zero, it goes down to a value over here, which is what we are calling the point B. So there is no current flowing right now because, of course, it's the y-axis. There is no current, and you have some magnetic flux in the substance, that is, the substance is not totally demagnetized. And this property of electromagnet or ferromagnet is called retentivity. That is, it has some retention, some memory that will linger even though you will remove the magnetizing force. That is, it will not lose all of its magnetism. And this comes very handy when we will discuss the shunt generators. This is the phenomena that we use in shunt generator, as we're going to discuss in chapter 4 or chapter 3, whichever. Now, to remove, let's say you want to remove all the retentivity, or you have an alternating current. The current is going back to zero, you still have some magnetism left. Now, when the current starts going again in the opposite direction, or if you want to make all the dipoles misaligned so that there is no magnetism left in the substance, you start giving some energy in the opposite direction, and finally at point C, all the dipoles becomes misaligned. That is, there is no flux density. So you need to supply this much energy right here in the opposite direction to misalign all the dipoles and to make the substance again a non-magnetic substance. And this is called coercivity, that is required for the magnet to lose its magnetism. That is, all the dipoles will become misaligned. That is coercivity. And as you keep suction, then of course the magnetism is going to happen in the opposite direction. It's going to go along this direction, and it's going to saturate in the opposite direction. All the dipoles are in the opposite direction, and again, if the current changes direction, When the magnetic field becomes, magnetizing force becomes zero, again there will be some memory, some magnetic flux left, and you keep moving in the positive direction. Eventually you will lose all the magnetism, but you will need some force to make it forget all the uh, magnetic memory that it had. And then again, if you keep supplying current in the positive direction, eventually it's going to saturate again. So this type of curve is called hysteresis loop. And hysteresis loop you're going to study here, you're going to study actually also in linear integrated circuits when we discuss comparators. But this is hysteresis loop. And this phenomena is called hysteresis, where you basically need some energy to set up the dipoles, and if you remove that energy, your dipoles are not totally misaligned. Then you're going to provide energy in the opposite direction to misalign all the dipoles. Keep going in the opposite direction, eventually it's going to saturate again, and so on and so forth. So this phenomena is called hysteresis, and the loop is called hysteresis loop. Now, due to, and again, all of this you can read what all of this is. What is the so hysteresis happens in every machine, because every machine has ion in which you have the current or flux. Current basically keep, if it's an alternating current, especially if it keeps changing its direction. So hysteresis happens in every machine. What is the result of hysteresis? Now there's another very good picture that I found online, and I put it this, and it describes everything all about the dipole stuff that I was discussing, that all of them are misaligned. Initially the material follow a nonlinear magnetizing curve, magnetized from a zero field value to a field value that is saturating. All the domains have been aligned, and then you can read this. It's a very good picture of exactly what I explained, exactly what's happening and why it is happening. So happens in motors, generator, transformers, anywhere. What is the result of this? So energy is required to set up the magnetic field, as we saw, right? You're supplying current, and we have to keep changing the direction of magnetic field in the core if it's an alternating current, that let's say, or if you want the magnetic field to lose its magnetism in one direction. Or when we are supplying this energy, or if this energy is supplied by itself, many times we don't intend to supply this, but since again you have iron cores in motor, generator, transformer and stuff, and most of the time you have the AC current, and in those iron core basically you have induced voltage. Those induced voltage run current, as we're gonna study, and due to that current, hysteresis happens. So due to this, we have a loss called hysteresis loss. And what is hysteresis loss? Basically, it is loss due to the energy that is supplied to the iron core to set up the magnetic field in one direction or the other direction, keep on going. And this setup, of course, requires energy. And whenever there is an energy, you have energy flowing in the material, which is a conductive material. You always have a loss in terms of heating of the core. So hysteresis basically produces heating of the core and results in hysteresis loss. In later chapters, when we will discuss the efficiency of the motors or efficiency of the machines in general, then we will consider hysteresis loss, but most of the time it is given to you. You don't have to go ahead and calculate with any equation or anything. How do we make sure that our hysteresis loss is minimum? And the way we can do that is if we can reduce this width of hysteresis curve. So let's say we make the core from a material that has a hysteresis curve which is very narrow, like that. The narrower the curve, the less amount of energy will require to misalign all the pole, and your loss is going to be very small. So instead of having using a material which can produce a wider hysteresis curve, we use material to produce a narrower hysteresis loop, and that results basically in less amount of energy loss and less heating of the core and less hysteresis loss. Alright, in the same video I'm just gonna discuss eddy current as well, because this is also something that produce loss in machines. So what are eddy currents? So in general, when you have core of the motor, generators, transformer which is made out of iron, of course it acts as a big huge short circuit. Now remember, in that core you have the magnetic flux which is linked with the core, which in general, especially if you have the AC motors, in general your magnetic flux is changing in general through the core. So when the magnetic flux changes, remember what happens according to the Faraday's law of electromagnetic induction: a voltage is induced in the coil. In this case, core is acting as a coil, a big huge coil which is short circuited. So what's going to happen? What happens is you have voltage that induce in this basically in the small circles. So the voltage is induced because, again, remember, it's a short circuit. A voltage is induced, and since it is acting as a short circuit, you have current start flowing in concentric fashion in the core. So you can see different currents are flowing: I1, I2, I3, I4, and so on and so forth. Again, why? Because the magnetic flux, which is changing with respect to time, is linked with the core of the machine, and core is acting as a coil or a conductor which is short circuit in nature. Voltage is induced and concentric current starts flowing. Now remember, whenever current start flowing, what's going to happen? It is going to produce heat in the core. Again, core has some resistance. It's a conductive material, so it has some resistance. It's going to start producing heat. Now these currents are called eddy currents, and of course, due to the eddy currents, core heats up, energy is lost. So this is called eddy current loss. So generally these two types of current, hysteresis loss and eddy current, these two type of losses, hysteresis loss and eddy current losses, they are called core losses or iron losses. Core losses or iron losses, and they are lumped under this category. When we discuss again the efficiency of machines, they will be lumped under core or iron losses, and generally their value is given to you. Now, how to reduce the loss due to eddy currents? What we do is to laminate the core. So we basically slice the core into thin pieces, and we insulate those pieces from each other and have laminated core. So when the core is laminated, eddy current will still flow individually in each core, but since now observe, it is so thin that the loss due to the eddy current is extremely small, and even if you add up all the losses, the total loss is going to be not as great. Actually, it's going to be extremely small as compared to if you don't slice it and have a big huge core which is acting as a short circuit and have concentric currents. So eddy currents are reduced, or eddy current loss is reduced by laminating the core, and that's what they do in practical machines. In transformer, motors, generators, everywhere is always made out of laminated material, whatever conductive material that they're using.